And here we are once more, chapter 4. So by this time, you may have already taken test number 1. So we're leaving behind for right now chapters 1, 2, and 3. Based on what we learned there, we're building up with chapter 4. Chapter 4 is going to cover atoms and elements. So we're going down from talking about substance and mixtures, everything we can see, to the world that we cannot see, the world of the atoms and the elements. And you're gonna be surprised when I tell you that your reality is not what you think. That you're right now not standing or sitting, that you're floating about 10 to the minus 8 from the surface that you think you are touching right now. And in theory, based on what we're going to learn about matter, in theory, you should be able to go through the wall. So think about that. Your reality is being challenged. So this is what we're going to learn on this chapter. So first thing I want you to realize is that everything around you, with the exception of light, because we said that light is not matter, right? Everything is made out of atoms and elements. And we're gonna see how we got that to that theory. Still a theory, so it could be that in the future we find out that we're totally wrong. But as of now, this theory allows us to explain everything around us. But it could be wrong decades or hundreds of years from now. So I want you to study what Thomson and Rutherford did that brought us to this understanding. So those are really two really important experiments. Then once we discuss those experiments, we're gonna go deeper into matter, like I said, and we're gonna talk about electrons, neutrons, and protons. And if this was a physics class, we will go even deeper than that, talking about quarks, quarks ups, quark downs, muons, but this is chemistry. We don't go that deep. So we're gonna stop at the electrons, neutrons, and protons. And then we're gonna see how we can relate this to the periodic table, how the periodic table organizes everything very nicely. And we're gonna see that also on the periodic table, we continue with our classification of matter in terms of groups, periods, and so on. After we do that, we're gonna see that the electrons, nature manipulate the electrons in the elements to make ion charges. And this is what's gonna allow us when we move to chapter 5 to understand compounds. Once we understand the atoms and the elements, on chapter 5, we're gonna put them together and we're gonna understand the compounds. So for that, we have to understand the charges first. And what we call an ion. So an element with a charge is an ion. And from those there, we're gonna come up with a symbol for what we're gonna call isotopes, because we're gonna see that matter is not clearly defined, that there's some variations within the same elements. And we're gonna call these isotopes. And we're gonna learn how to play with them by looking at the isotope symbol to be able to determine the number of protons, the number of electrons, and so on. And then we're gonna see that there's a special number in the periodic table, which we call the atomic weight, which kind of contradicts what we're gonna learn about protons and neutrons. And we're gonna see why. And this is gonna be, once more, related to the isotopes. So this first part of the lecture, we are gonna cover most of what the concepts that we are gonna be talking about, and we're gonna begin with recognizing that all matter is composed of atoms, so basically re-emphasizing this theory on our knowledge. And this is the visualization I would like for you to see. Whenever you look at anything, if we look at way past the microscopic level, remember microscopic level is 10 to the minus 6, so we're talking about 10 to the minus 9 or 10 to the minus 10. So when we go down to that level, 10 to the minus 9, 10 to the minus 10, that's where, in theory, we start seeing the atoms. So every time you see any piece of matter, try to visualize it that is composed of atoms. And atoms are going to be, like we learned before, the smallest you can go that still retains the properties. Like this is copper, So this is the smallest you can go that it will still have the same melting point as copper and all of those physical properties. So begin visualizing everything like made out of little tiny particles, and we're gonna call those atoms. And if all the atoms happens to be the same, then we're talking about an element composed of many atoms of the same. So back when I was doing my undergraduate degree, the theory was that we would never be able to see the atoms because they were beyond our capabilities. But guess what? We're gonna call this instrument that you're seeing here a tunneling microscope. And this is one of the last advancements in technology within the last 10 to 20 years. And with this, applying that theory that we know, we are now able to see atoms. So everything I was told that we were not able to do, we are doing now. But also I have to let you know that when I did my undergraduate degree, the periodic table only went to number 103. Nowadays, it goes to 118. So we're advancing really fast. You will be amazed on how much we're advancing that we don't know about it. The news don't tell you about that because it's not really dramatic like they like to do on the news. So we're doing a lot of really good things that people don't know about it. So notice that this scale is at the nano scale. So we're seeing atoms at the scale of something like this would be 2 nanometers. So from here to here, about 2 nanometers. So this molecule would have probably, I would say, really rough estimation, about 4 nanometers across. So like I tell you, we're talking at a really small level. This is actually molecules of carbons, 6 carbons, making a ring. So nowadays we can see that, so which is really amazing to me. So for those of you that have watched the Matrix movie, this is kind of the idea that I want you to put on your mind. From now on, every time you look at anything, try to visualize it like made out of really small particles all together there. They tend to accumulate more to one side than the other, probably, but it's all made out of particles. It's just an analogy that I like to use when I think about atoms. And that's as much as I can give you about recognizing that matter is composed of atoms. Just asking you to visualize it like that. And remember, it's a theory, a very strong theory. It's not a law. So who knows? Who knows what we discover next 10, 100 years that will make us say, wow, that really worked, but it was wrong. Or yeah, that's going to have to become a law now because it's been 100 years and it's still holding. So the next objective will be to truly understand how we got to that theory. We had to study the experiments done by J.G. Thomson and Rutherford. And as you can imagine, they didn't do this by themselves. They had their research team, they had their graduate and undergraduate students working for them. So it's a combined effort like everything, but they are the ones in charge of those groups, so they got the credit for it. I'm not gonna try to explain those experiments to you here because I have 2 videos that explain that a lot better of what I can do for you. Those are posted in Canvas, so make sure you go and watch those 2 videos before you continue. You can put this on pause and go and watch those videos. Once you watch those videos, then make sure you answer these daily works. So now that you're back from watching those videos, because if you don't watch those videos, then the rest is not gonna make too much sense to you. Now we're gonna talk about the electrons, neutrons, and protons that you saw how they were discovered by Thomson and Rutherford. So we're going to talk about the properties of the electrons, the neutrons, and the protons, and we're going to see that they are also described by the charges they possess. And this is what I would like you to see, how as you saw from the Rutherford experiment and Thomson's experiment, we came up with a model that tells us that the nucleus is at the center of the atom. So this will be, it's not as solidly defined like a ball. It's kind of a spread. So out of the atom, most of the mass you're gonna find it right on the center, and we're gonna call that the nucleus. That's where the mass is. And then around that nucleus, you're gonna find the electrons. And let's fill out this table so you have an idea of how to compare there. We're gonna be talking in terms of mass. We cannot be talk about grams at this moment because these are really small particles. So we're gonna talk about atomic mass unit. Once we go into chapter 5 or 6 and we start talking about the mole, I will come back later and let you know with a better knowledge what an atomic mass unit is. As of now, it's just a unit that we use for the mass of the atom. So the proton have an atomic mass unit of 1. The neutron have an atomic mass unit of 1 also. So that's what they kind of look more or less the same size. And the electron, we're gonna say that the electron have no mass. But realize this is a lie. The electron have mass. However, is 1/10,000 of the mass of the protons and the neutrons. So for all practical purpose, we tend to say that the electron doesn't have mass. And the analogy I like to do is this, so we can truly understand why we say that it doesn't have mass, but it has mass. So it's not a lie, it's just basically an assumption. We're gonna assume that it's basically its mass doesn't count. And this is the analogy I like to do. If you have an elephant and I tell you to put it on a scale, and the elephant weighs, I have no idea how much an elephant weighs, but let's say that it weighs 25,000 kilograms. And I'm gonna tell you, I'm gonna put this elephant on an airplane. So it's super important that we know exactly how much the elephant weighs, so we know how much gasoline to put, how much higher we can go, how many more people we can put in there. So it's super important that I have a true meaning of the weight of the elephant. So I weigh my elephant, and I take my elephant up the ramp of the plane. And before the elephant gets in there, a flea flies off. Would you stop the operation and say, stop, a flea just flew off the elephant, we had to weight the elephant again? And the most logical reason would be, no, we're not gonna weight the elephant again. A flea is insignificant in respect to the weight of the elephant. So that's how the electron is. It does have mass, but it's so insignificant, like one of 10,000 of the proton or the neutron mass, that we consider that the electron doesn't have mass. So that's why we say that all the mass of the atom is concentrated inside the nucleus. So the nucleus contains the mass of the atom, because we're not counting the electrons. So that's the first thing you have to know. That's what we're going for. In addition to that, we're gonna say, let me clean this up a little bit, that the proton, and this is based on what Thomson and Rutherford found out, that the proton have a charge of +1, the neutron have no charge at all, and the electron have a charge of -1. Exactly the same magnitude as the proton, but opposite charge. We know that the proton is located inside the nucleus, or is what makes the nucleus. It's not such thing as inside the nucleus. The proton is the nucleus together with the neutron. And the electron is going to be outside the nucleus. So what else we can say? Well, I want you to put this on your mind. I know this is an introductory class, but it could be that some of you probably have to eventually take science majors, chemistry 1, chemistry 2, and probably organic chemistry. And if you ever take organic chemistry, people say that this is the hardest chemistry of them all because it's so hard. That's not true. It's actually the easiest one as long as you know the secret of life. The secret of life is going to allow you, if you ever take organic chemistry, to instead of memorizing 2,000 pages of reactions, to probably do like 100, and everything else you can think about it without memorization. And this is the secret of life. Negative, love, positive. So negative will always be attracted to positive. Positive be always attracted to negative in terms of charges, which means negative and negative are gonna repel each other. Positive and positive are gonna repel each other. So think about that so that we can understand the atom. With that said, remember the secret of life, negative, love, positive. Let's look at the nucleus again. So what do we have on the nucleus? We have protons and neutrons. And we know that the protons are going to be, let's say that the blue one is the protons. So the protons are going to be positive, positive, and positive. And what did we just say about the secret of life? Positive, love, negative. So positive and positive, that's really bad. Positive and positive doesn't want to happen, but it does happen. So what we understand from the theories that we know, including quantum theory, is that the function of the nucleus, on a very simplified way, is to hold those protons together. So those protons in the nucleus, even though they want to repel each other, they're held together by the nucleus. We call that the strong force. It's keeping them together. That's why it's such convenient that the neutrons have no charge. And what about so we know the function of the neutrons, the strong force holding the protons together. What about the electrons? Well, electrons, we said that they are negative, right? And we're going to show it like this. And the protons are positive. So the electrons are going to be attracted to the nucleus. So why are they not like a magnet in top of the nucleus? Because there's a lot of other things that we don't cover on this course, like the law of relativity and the movement of the electrons, that allows them just to be at a certain distance from the nucleus. Same thing that happens with the moon and planet Earth, with planet Earth and the sun, with the sun and the galaxy and the black holes, stuff like that. So because they're moving, they do not fall, they tend to keep like an orbit there. So the electrons are going to be located as close as possible to the nucleus because negative, love, positive, but they're not going to be crashing against the nucleus. If they did, life as we know it would not longer exist. So, so matter is neutral. So when you walking through your house, you don't feel suddenly attracted by the wall. So there's not an attraction between matter. Matter, for the most part, is neutral, which means if matter is made out of atoms and atoms are made out of protons, neutrons, and electrons, the overall charge of all that has to be neutral. So because the electrons are -1 and the protons are +1, that tells us that the number of electrons has to equal the number of protons. So that's a very important concept. Since matter is neutral, the number of protons on an atom will have to equal the number of electrons on the atoms. What about the neutrons? Who have to be equal to the neutron? Well, the neutron is going to be very close. Remember, the function of the nucleus is to hold all the protons together. So it's going to be very close to the number of protons, but it doesn't have to be the same. I can actually have an atom of carbon and another atom of carbons, and both of them can have a different numbers of neutrons. So the neutrons can vary from atom to atom, and they don't have to be the same as the protons. So we're gonna learn very soon how do we find out how many neutrons we have. So let's see. Let me see. There's something else that I need to tell you about the atomic model. Remember, this atomic model came from the experiments from Thomson and Rutherford that at this point you have already watched. If not, stop, watch that first because you're gonna get lost. And like I said before, 99% of the mass is gonna be located inside the nucleus. So we say for our practical purpose, all the mass is on the nucleus. And now I wanna kind of tell you what I told you at the beginning of this lecture. The reality as you know it is very different from what's really happening. This model, so let me clear the screen a little bit. This model that I'm showing you here, this model here of the atom, that's the best you can draw it, but it doesn't represent the reality. Imagine this. First thing, the nucleus, you will not be able to see it like that because those protons and those electrons are so together that all the mass is going to be concentrated on a very small area. So you already know about density. And remember this, if I have a cube that measures 1 centimeter everywhere you go, that's 1 cubic centimeter, which is the same as 1 milliliter. And if we fill it up with water, it's going to weigh 1 gram because the density of water is 1 gram for every 1 milliliter. So imagine now something that is 1,000 grams for every 1 milliliter. That would be something 1,000 times denser than water. Imagine this one now. Something that is 1,000,000 grams for every 1 milliliter. At this point, I cannot even imagine that. I mean, how can you imagine 1,000,000 grams? That's like hundreds and hundreds of pounds in 1 cubic milliliter. So here's the kicker. The density of the nucleus is on the order of trillions. Trillions of grams into 1 milliliter. So proportionally, we know that the nucleus is really small. It's to the nanometer scale. But if we can measure it on cubic centimeters, it would be equivalent to about 1,000,000,000,000 grams. So the density of the nucleus is beyond comprehension. And imagine those protons being held together in there at that density. Imagine the force that you have to keep to maintain those protons together in there. And you don't have to imagine much. How many of you have ever seen a video of a nuclear bomb? What do you think we call it a nuclear bomb? because it's based on the force that is holding together those protons on the nucleus. So all that force, when we manage to detonate a nuclear bomb, all that force that is holding those protons together, that's what is being released. So imagine all that force that is keeping all the matter around you together. In addition to that, I want you to think about something else that Rutherford said on his experiment. He said that most of the atoms, so this is the atom, right? So this is the atom. Most of the atom, so all this here, all that in there, most of the atom is empty space. So if most of the atom is empty space, as you saw in the Rutherford experiment, if you try to throw something through the atom, most likely it will go through. Most of the time, it will go through unless it hits the nucleus. So how come when I touch the wall, how come my hand doesn't go through the wall when most of the wall is empty space? Think about that. All matter that you see around you, more than 90% of that matter is empty space, but your hand doesn't go through. And I also told you at the beginning that you are not standing on the floor right now. And if you happen to be sitting, you're not sitting on the chair right now either. You are floating on it. And here's the reason. So the nucleus is right here on the center. So what's on the outside? On the outside, you're going to have the electrons. And the electrons are what charge? Negative, right? So if this is what your floor is made of, so everything that is exposed on your floor on the surface is gonna be negative charge. And then you're trying to sit or stand on the floor, and this is gonna be you sitting on the chair, right? The chair is negative all on the outside, and you are what? You're also negative. And what is the secret of life? Negative, love, positive. What about negative and negative? They repel. So you are being repelled by the chair. You are being repelled by the floor about 1 times to the minus 8 meters. So about 1 time to the minus 8 between you and the floor is empty space where you're floating on it. So when people tell you, wow, you look like you're floating through life, you say, yeah, all the time. I always float through life because that I never touch anything. Everything is repulsions. So going back to the wall, how come my wall cannot go through the wall? Same reason. Here is the wall. Here is your hand, right? Your hand is made out of atoms, and on the outside of every atom is the electrons, and the wall is the same story. So when you come to touch the wall, the matter from your hand is being repelled by the matter of from the wall, and that repulsion, that force, your brain interprets that as a solid. The stronger the repulsion, the more solid something is going to be believed to be to you. So the reality, as you know it, is a lot more complicated of what your brain tells you. It's our reality, so we live with it, we understand it the way it is. But it's just an illusion caused by the repulsion of the electrons and the protons, as simple as that. The charges of the atom tells you reality. So once more, before we leave this slide behind, the mass of the proton, 1 atomic mass unit. The mass of the neutron, 1 atomic mass unit. So protons and neutrons are more or less the same mass. The electrons, we're going to say that it have no mass, but it does. Charge of the proton is positive. Charge of the neutron is not charged. And charge of the electron is negative, same magnitude as the proton. And you have to have the same amount of protons and electrons for matter to be neutral, which most of the matter is. And the location, protons and neutrons, they're going to be located inside the nucleus. And the electron is going to be located outside the nucleus. So with that said, just go ahead and do that daily work. And when you're done with that daily work, we proceed with this part. Well, actually, we summarize this part. So we talk about the properties and charges of the electrons, neutrons, and protons, and we just finished summarizing them. New objective, determining an element's atomic symbol and atomic number using the periodic table. And once we use the periodic table, we also going to use it to classify the element by group. So we're going to see what all that is all about. So here's the periodic table. So let's look at the periodic table briefly. If you look on the left side, you're going to see row number 1, row number 2, row number 3, row number 4, 5, 6, and 7. So there's 7 rows. Yeah, well, there's 2 more below, right? Well, let's be careful about this. This is number 56. This is number 72. So why so big a jump? Because 57 to 71 are supposed to be there. So this still is row number 6. However, they have a unique set of properties, so we put them separate to indicate, based on that sequence of number, they're supposed to be there, but their properties are very unique, so let's put them by themselves. The same thing happened between 88 and 104. They're supposed to be there, but they are here, so this is row number 7 too. So that's one of the first things I want you to realize, that the periodic table is organized by rows, and they have numbers. And you saw the numbers, right? The numbers are right here. 1, 2, 3, 4, 5, 6, 7, and this is 6, and this is 7 also. But in addition to that, they also have numbers on top. So the periodic table is organized by rows and by columns. On the rows, what we are seeing is that this number increases as we go from left to right. So what about the columns? Well, the reason of the columns is that most of everything that is on the same column, they are gonna share properties. So the reason they are on columns is because they behave very similar, like a family. So we call those columns groups. So the columns are gonna be the groups. And on the old times, like when I was doing my undergraduate, we used to call them families, and some people still call them families because they look similar, they behave similar. So the rows, we're gonna call those periods. So the periods go from left to right, and if this was on the English language, if I say my name is Luis, I'm writing from left to right in the English language, right? And if I'm doing a sentence at the end, I put a period. So left to right, period. So left to right, we call those periods. Top to bottom, we call those columns. The reason for the columns is that we have the elements that have similar properties on those columns. The reason for the period is that they show a progressive numbers on the number that we see there. By the way, that number that you see there, like this one here, 27, we call that the number, but not just the number. We call that the atomic number. So from now on, when I said, what is the name of atomic number 30? Ah, you're going to say, oh, 30, that's zinc. So atomic number 45, that's going to be rhodium. This number here, we're going to call this the atomic weight, and we're going to talk about that on the second part of this lecture. So we're going to see where the atomic weight comes on later. So let's continue talking about the atomic number. The atomic number happens to coincide with the number of protons, which means the atomic number is also going to give us the number of electrons, because as long as we're talking about a neutral element or neutral matter, the number of protons equals the number of electrons, right? So the atomic number, the number you see on the periodic table, the whole number, not the one with the decimals, the whole numbers, that's going to be the same as the number of protons, which tells us the number of electrons also. So what else I can tell you about the periodic table? We talk about the periods, we talk about the group or families, we talk about the atomic number. I told you we're going to talk about the atomic weight later. And then we got the symbol. So for example, lithium is going to have that symbol. So the symbol of all the elements as we know them today, they always are going to be a capital letter or a capital letter with a lowercase letter. I would say better representation, something like this. They're gonna be, most of the time they're gonna be different. So the elements are always gonna be a capital letter or a capital letter with a lowercase letter, like a capital letter by itself or a capital letter with a lowercase letter following that. By the way, when we write the numbers of the elements, like tungsten, for example, when we write those on a sentence, they do not use capital name. We do not consider name common names. So unless you're starting a sentence with an element, never put a capital letter on the actual name of the element. And let's see. So that's all I'm going to tell you about this slide so far. So remember, periods left to right, where the atomic number is increasing, columns top to bottom, because the elements share similar properties, and they are organized by groups or by families. Another very important organization we do with the periodic table is to differentiate which elements are going to be metals and which are non-metals. And we do that by looking at the periodic table, go to where boron is, and we're going to do a line right there. And then we're going to start drawing a set of steps. So beginning at the left of boron, go down every block and do a descending step. So any element that happens to be on the left side, we're going to call those metals. Any element that happens to be on the right side, we're going to call those non-metals. And that's extremely important to be able to do that when we go into chapter 5 to start making compounds. So, but nothing is as clear-cut as this in chemistry or any other thing. So there's some exceptions. The elements that are actually touching the steps, let's make it with this one. The elements that are actually touching the steps, like that one, that one, that one, that one, and on the other side also, with the exception of this one. So this one is aluminum, and we know that aluminum is a metal. So all the elements touching the steps, at least toward the top section, except aluminum, are what we're gonna call semi-metals, or, which is the one I like to use, metalloids. And they're called like that because since they're right on the boundary between metals and non-metals, they tend to have both properties. So they are not really like metals, but they are definitely not like gases. So they share the properties of non-metals and metals. And we call those metalloids, like a humanoid. A humanoid is something that is like a human, but not really a human. So the non-metals are gonna be, excuse me for a second. So the non-metals are gonna be the one to the right of the steps. The metals are gonna be to the left of the steps, and the ones touching the steps are gonna be the metalloids. So that's a division that we do in there. So going back to the groups. So the groups are gonna be my columns. So important groups to know. These are gonna be my noble gases. These are gonna be my alkali metals. Notice that I didn't include the hydrogen because I know the hydrogen is a gas. We're gonna see why they are located there later. All of these are gonna be my transition metals. And these are also transition metals. But remember, they're supposed to be here. So to differentiate them, we're gonna call this the inner, because they're supposed to be on the inside, the inner transition metals. And these are also important. We're gonna call these the alkaline earth metals. All other classifications I do not consider that relevant. So these are the ones that are really relevant. And with that said, go ahead and complete daily work 4.4. Daily work 4.5. And after you do that, we have talked about the atomic symbol. You know that the atomic number now is the number of protons. You saw the organization of the periodic table between groups and periods. The groups are also the family. And we began to classify them by the different groups, like the alkali metals, the alkaline earth metals, the noble gases, and there's another one I forgot to mention. These are also important. These are gonna be my halogens. A lot of the materials we use on our society are gonna be based on halogens. So groups to remember: alkali metals, alkaline earth metals, the halogens, the noble gases, and the transition metals. And we are gonna leave it there for right now. So when I come back, we will continue going deep into the atom. We will talk about the charges, the ions, and then we will talk about the isotopes, and that will close the chapter. So until the next one, see you soon. Bye-bye.